Hello everyone, my name is Chandru. I'm a software architect at Bet365. Um, I'm going to talk about a few lessons learned while rewriting a PubSub system in Erlang. It was previously written in Erlang, but we wrote it again because code accumulates craft over time. And so, firstly, a little bit about Bet365 in case some of you missed it yesterday when my colleague Mike talked about it. We were founded in 2000. It's a privately held company located in Stoke-on-Trent in the UK. It's the world's largest online sports betting company. Um, Over 19 million customers. And it's a very technology-focused company. The secret for the success really is their success in harnessing new technology as it becomes available. And Bet365 really likes Erlang. It completely believes in the whole redundancy model. So we have actually two principal software architects. I'm the good-looking one. So a bit of a history of Erlang use within the company. I've joined recently, but Bet365 started experimenting with Erlang in about 2011. So far, there have been 3 major systems written in Erlang, and there's a 4th one in progress. The code base, as you'd expect, is of varied quality because when you first pick it up, traditionally it's been Java and .NET with lots of Microsoft SQL Server. So some of the first code bases look what you'd expect someone coming from a Java background and object-oriented background writing Erlang looks like. So I'm going to talk about what we call the publisher internally. It's a fairly, well, on the face of it, it's a fairly simple system. There's a bunch of databases which are data sources within the business. There's a system called a data pump, which basically collects all this data and pushes it through the publisher onto, well, all the customers using various devices. I'll just quickly show you what it's doing. So typically, if you go to the home page, and let's say if you look at in play, if you look closely, you'll see some of these figures changing, or you see that top right, it's sort of showing you how the game is progressing. Pretty much every change you see on this website is this change being broadcast to every connected client in real time. So as you can imagine, I mean, with about 2 million customers concurrently connected at peak times, there's a lot of traffic going out. And that's what the publisher handles. So why rewrite? Hopefully this slide will explain to you. This is showing the internal process structure before we did the rewrite. So there's a data pump. There's a socket handling process, which is this is a single socket through which all the data comes. And every oval you see here is a process. So it goes through decode stage 1, and then it went through a decode stage 2, and then it went through a decode stage 3, and then it went through a stage 4. You can imagine how many will fit in the slide, right? So it went to 5, and then it went to another decode stage 6, and then it went to a pool of processes. Again, the number of processes selected was a fairly finger-in-the-air number, as in, okay, let's choose about 400 processes and see if that deals with the load. And that farms off work to another pool of post-processes, which then send it off to the client. And that's the simple version of it. If you try to translate this into code, it can get a bit. But the biggest problem was it's a complicated process structure. So every time you wanted to make a change in it, it sort of gets harder. And there were message queue hotspots because between each of these processes, we were using Erlang message passing. So if any one of the decode stages slows down and the previous one is slightly faster, you get these message hotspots. While while it sort of deals with it, and even if there's a message queue build up, it catches up. It can lead to instability, which is sort of sort of unpredictable in nature, which is not great. So we decided to rewrite it from the ground up. So the first thing we did was looked closely at the data. Basically, the data we're shipping out to clients is essentially a very large tree. And the number of nodes in that tree is about 2.2 million nodes in that tree. And but if you look just below the root, there are about 130,000 top-level nodes. And all these are independent of each other. So actually, there's no dependency between them. So the natural thing to do in Erlang is obviously, so what we did was, okay, the data source was a single socket. There's no way we could have changed any of that. So you have a single process to take a message of a socket, decode it, update global state in ETS. But then we modeled each of those 130,000 top-level nodes as a process. So it looks a bit like this now. So the first attempt was we had a process taking messages off the socket, decoding it, updating global state because we need that, and spawns 130,000 processes. And then we have one process per TCP connection from the client. I mean, typically our clients use TCP connections if it's a Flash client, but if it's web-based plain HTML clients, then they use HTTP. So we model it as one process per client so that we get nice isolation. Because one of the problems we had with the previous implementation was that because we had pools of processes dealing with pools of customers, if one of them was on a slow connection, it affected everyone behind it. Whereas now you could have a process per client, and if one of them slowed down, that's fine because the rest of them carry on. So that the first attempt actually sort of worked well, but the problem was message queue was building up at source because that single process which is taking messages off the socket couldn't decode it fast enough, do everything that it was supposed to. It was heavily loaded. It didn't cause instability in the system because you have active ones optioned on the socket, which means you won't get overloaded, but it just means you're really slow and you're not keeping up. So we just slightly tweaked it in the second attempt. So I did make a lot of fun of the number of decoding stages I had, but I had to eat a bit of humble pie and say, okay, fine, we'll have one extra decoding stage in there just to cope with the. So that's what it looked like in the end. So really, one process was taken off the socket, putting it into an ETS table, and then there's another process which was reading it off as fast as it could, and then doing the rest of it. I mean, I consciously chose not to use message passing between the two again because the socket handling process could read faster than the decoding process could keep up. And ETS acts as a nice buffer in between. All that you use up is a bit of memory, but you don't get instability. Because one of the biggest, with Erlang message passing is that it's really powerful, but once you get a process which message queue is building up, it sort of all goes haywire and the system performance becomes unpredictable. So we have these data sets which we capture during our normal operation, and we test with that. So, but this tree size grows with time as we add more fixtures which we trade on. So it worked well with about 1.8 million nodes in the tree, but throughput and latency fell for 2.2 million. And we couldn't quite understand why that is, because it's just a few more processes. It should have just worked. So then we started looking at what was possibly the cause of it. We thought maybe it's garbage collection slowing down the system. So we thought we'd investigate that. And garbage collection isn't one of those things you really think about in Erlang because it hardly ever is an issue. So I had to sort of dig into the manuals and ask on the mailing list to say, to try and understand it. And actually, there was a few surprises in there. So, GCs per process, great. That's no surprise. That's fine. And again, regular GC of a process is sort of generational. So every Erlang process has an old heap and a new heap. And data that survives at least one GC is put on the old heap. And finally, when there's no space on the old heap, a full sweep is performed. But the surprising thing was that the time taken to garbage collect eats into the 2,000 reductions available for a process. That came as a big surprise for us. I mean, once you know this and you think about it, it probably makes sense because you'd think you could do it either way. But it's sort of, you can understand why that is. But it came as a surprise. And but the implication of this is that if you have a busy process, a process in your system which you can't parallelize, if you like, or you can't make concurrent because you've got to handle messages in sequence, and it produces lots of garbage, then it'll quickly spiral out of control because the more garbage it produces, it's got fewer reductions to actually do its work. But actually, it's a busy process. There's a lot of work coming in. So you're stuck in this cash-ready situation where, So once we knew about this reduction count penalty, that if you actually do a longer GC, then actually your process is being penalized. We thought, okay, let's see where else, how else does a process incur reduction count penalties? So, I mean, the first one we knew already, so that sending a message to a process which already has a large message queue, you're penalized for it. And so the other thing we found out was if you have a long GC, then again, your reduction count is penalized. So when we started looking through the Beam code, it found out that actually your reduction count is also affected by the size of message you send to another node. So if you're using RPC, say, for example, and you're sending a big message across, at least from the way I read it, it seems like your process is going to incur a penalty. And if you're doing a lot of that, you might see your process slow down with no obvious explanation that it's happening. And it also seems that actually it's proportional to the size of binaries which are created, which your process is creating. Again, none of this was really obvious or well-known. And there's lots of other places where reduction counts are being adjusted. And I'm not really sure what exactly they're being adjusted for. Because the manual says a reduction roughly equates to a call to a BIF. I think that's what it says. So it'll be nice if we had some documentation which says, if you're doing this sort of thing, like the efficiency guide we have in Erlang, if it said, if you do this, this is the kind of penalty you're going to incur, so that it helps in the design of our processes to say, okay, if that is incurring a penalty, I'll design the system slightly differently. So I mean, I do appreciate the OTP team's point of view that actually is an internal implementation detail. You shouldn't have to know about it. And for the vast majority of cases, when you're writing Erlang software, actually you don't have to think about this. But when you're sort of pushing for the maximum performance you can get out of a system, it's helpful to know, because it's not just performance penalty, because some of these lead to instability in your system as well. So if you remember the process structure, there's one process which is dedicated to reading messages of the socket, and there's another process which is dedicated to decoding messages it's receiving. So with I hadn't used this process priority flag for a long time, and I thought, I know what I'll do. I'll just make it a higher priority process, and that should automatically give me more processing power, and I can keep up with the fire hose coming in. But actually, priority height does not really mean you've got more reductions. All that it means is that you'll get scheduled before the others, and again, it's if the process has work to do, which translates to have you got any messages in your queue. So you can't really have a process busy looping. I mean, one of the ways to do busy looping is you just say receive after 10 milliseconds, wake me up again. But actually, that's the timeout. There's no message in your queue. So it doesn't really help. I mean, so I just thought I'd point out, the process priority isn't really what you think it is. But what would be nice to have is for us to be able to specify that there are certain processes in the system which are going to be very busy because we know they're going to be very busy. And can we have, I mean, currently we're running these publishers typically on 24 core boxes. I think pretty soon we'll probably be running them on 40 core boxes. In which case I can quite easily say, you know what, I've got 2 critical processes which I need them running all the time because they're going to be busy. It would be good to say, actually, don't impose the 2,000 reduction limit on it. Just dedicate a scheduler thread because I've got 40 to spare. And this sort of ties in with what with Costas and Magnus's presentation yesterday, where if we start having access to chips like the Epiphany, where there are tens, if not hundreds of cores, it's cheap to then just say, well, just dedicate a few cores to these processes of mine because I've got loads of them. But yeah, that's currently not possible. So none of these things really explained what was happening in our system. It didn't explain why our system was slowing down when suddenly we had a bit more data. It's not a lot. I mean, from 1.8 million nodes in the tree to 2.2 million, it wasn't a lot. So so we still had no clue. But one thing we noticed when we were running htop on the box was on a fairly regular basis, pretty much all the beam threads would go into an uninterruptible sleep state. It sort of shows up as a D in the process state when you look at the process listing. And I wondered what that was about. So we tried to see what was causing this. So we're looking for processes which were entering that state. And along with our beam process, this particular one kept showing up on a regular basis that again, I didn't know what to make of it, so I thought I'll search for what k-huge page D is. And it turns out that k-huge page D implements something called transparent huge pages on Linux. And if you look up the Red Hat documentation, it says it's a feature in 64-bit Red Hat Linux. It's enabled by default for all applications. And it's an abstraction over what's called huge page support in Linux. And again, I hadn't heard anything about any of this, THP or so when digging. The first thing you notice is actually most database vendors recommend that you turn this off before you install their database because it's not going to work. I mean, that goes for Oracle, TokuDB, SAP HANA, all of these guys. So we thought, okay, something there. So what are huge pages? I mean, yeah, once you look at it, it's fairly obvious. The typical size of a page in memory is 4 kilobytes. But nowadays, with servers with lots of RAM, 20 gig of memory equates to 5 million pages, and that many entries in the page table. And these entries are typically stored, I think, in the layer 2 cache, which has limited memory. So if you don't use these huge pages, suddenly you're having to do this, store this information in main memory, which slows it down. But Red Hat kernel allows page sizes of 2 meg and 1 gig, and they recommend basically that if you've got memory main memory in the order of gigabytes on the box, you use a page size of 2 meg, or if you got terabytes of RAM, then you use page sizes of a gig. So how does this transparent huge page work? Because using, I mean, the reason Red Hat did this, developed this transparent huge page support was because using huge page support requires a lot of change to your application itself. You've got to plug into the APIs it provides, and it's non-trivial. So Red Hat developed this THP so that most software which runs would be able to benefit from it. And according to their website, it says it aims to make it just happen. I think it also does some memory defragmentation when you start hitting high memory use, and actually, which kind of tied up with the fact that we observed it when the memory usage of Beam exceeded about 20 gig on a box with 32 gig of RAM. So, well, we did what everyone was recommending and turned this thing off, and performance instantly improved exactly to how we'd expect it to. I mean, I haven't really investigated in quite a lot of detail exactly how it affects Beam, but all I know is that actually disabling this made our Erlang system work as we expected it to. So just for the record, if if any one of you has similar problems, you can just copy paste that, which is what I did from Stack Exchange. So that's how you can permanently disable it on your box. So yeah, I mean, it took quite a long time to get to this. It probably took nearly a couple of weeks to get to the bottom of why this was happening. I mean, so now we're looking at things like system tap to see actually, can we, again, this must be something which most people suffer from. I mean, when I went through the whole troubleshooting process, I felt after 2 weeks when I finally solved this, I thought someone else must have solved this problem, right? How come I never heard about it? But if you're running some software on a general purpose server, there's really only 4 things you're really interacting with. You're interacting with the network, with the disk, the main memory, and the CPU. It should be easier to monitor things like this from an external point of view. I think an operating system like Solaris had dtrace where it was quite easy to, well, not easy, but it was very well instrumented for detecting these kind of things. But I think it is possible on Linux as well now with system tap. But again, there's not a lot of awareness about it. When I mentioned about the instability in the first version of our system caused by message passing, I see this so often in a lot of Erlang systems that message passing is great when you first encounter it. You can just write. I mean, I think when I attended the first training course for Francisco a long time ago, we had a database server running in about I don't know, a couple of hours. Hey, look, I can write a database in a couple of hours. But actually, when you start to scale it up and you want to use message passing in anger, what I found at least is that unless you're really careful, you can easily kill yourself with it because it's so powerful. But there's no way to as a receiver of a message, there are no mechanisms to control it. Any process can stick a message in your mailbox, and if that mailbox grows big enough, your process is, well, doomed. So what we did with you just using plain Erlang code, and it's nothing fancy. I wrote a mailbox process for every process, which sort of gave what is similar to active ones semantics on a TCP socket. And the really surprising thing was actually there was no improvement in performance, sure, but actually there was no degradation in it, which speaks volumes about Erlang's capability of dealing with massive number of processes. So, and the way it was that, So every worker process which wanted this kind of active once mailbox, what it would do is it spawn a mailbox process and store its PID in ETS, and anyone who wants to send it a message would look up the ETS table, get the PID, and send it the message, send the mailbox process the message. Now, the mailbox process just accumulates in a queue data structure in its state, and every time the worker process actually said, okay, I'm done with this, give me the next one, it would just call similar to how you do it on a TCP socket. I thought the performance would suck, but actually it made no difference at all. It just used up a bit more CPU, but actually it just carried on. And this worker process is one of those 130,000 processes, which means I actually had 260,000 processes just dealing with these nodes, and not counting the process per connection towards the client. So the results of finally after we fixed all the issues. So this graph is showing the latency of a big. I mean, latency is important to us because any update, say our traders are doing, like changing the odds for a bet, we wanted to get it out to the clients as quickly as possible, so they see those changes. So this graph is showing latency for messages for 100,000 clients connected at 1 times our production load. That is basically the production load we were experiencing at that time. So, and that's on a log scale. So you can see the vast majority of it are well within the 100 millisecond range. The regular spikes you see are, we basically had log data of a 2-hour window. So we were replaying a 2-hour window of a busy Saturday. I come from the telecoms world where you dimension your network in a way that you can sort of gracefully deal with New Year's Eve spikes and Christmas spikes. In betting companies, you got a Christmas every Saturday because Saturday afternoon is the time when all the sports are kicking off, football is there, and traffic just goes through the roof. So just spreading that out a bit, just to show you really what more fine-grained view of that latency. Those spikes you see are basically because we have a 2-hour window of data. Every 2 hours, the system which is simulating the data source drops its connection, which means, and then it's just an oddity of our implementation that what it first does is when it first connects, it gives a shed load of data. And that again, we are able to read the data faster off the socket than we can actually process it. And that's where you see these spikes of latency because all this is accumulating in the ETS table and the decoding process is slowly catching up. But at least it doesn't cause instability in the system because ETS is acting as a buffer for the data and we don't have processes building up message queues. I tried the same test with 100,000 clients, but 4 times production load. And actually so you've got a longer window where, you see that big 10-second or more than 10-second latency, or much more than 10-second latency, over a period of several minutes because it's trying to catch up. But actually the system runs with a very repeatable pattern. Okay, I've got this big spike, I'll slowly chug through it, but then the rest of it, again, the latency is back to within 100 millisecond level. So it just goes to show that it doesn't kill the system. It goes slow, but that's the best you can do under a massive spike, that you don't die, but you just handle it gracefully. So again, bottlenecks within this system, like I showed in the graph earlier, the queues build up at very high load, but that's there really as a buffer to absorb these spikes. The only way really I could think of to solve that is by changing the protocol we have between our data pump, because it's kind of it's not very efficient, but that's legacy reasons. It's And at a higher load, some of these processes actually become quite hot in terms of, because they're actually doing quite a lot. They're handling all the messages coming in, they're maintaining a data tree internally, and they're then, each of these client processes, they could all be subscribing to a single one there saying, actually, I'm interested in that. And you've got thousands of these saying, I want that. So some of these can become quite hot. But the nature of the problem is we can't make it anymore. We can't throw more processes at it. We have sort of put in some hacks, but yeah, it's without changing our end-to-end protocol, it's sort of hard. So yeah, I guess the more interesting thing is to describe some of the work in progress we have. So I'm working on something called what I call a distributed data grid. It came about because of a request from one of our development team, because basically he wanted, I don't know if you're familiar with something called InfiniSpan. I think it's in the Java world. It's basically it's a map data structure in memory, but it takes care of replicating it to basically n number of replicas. I have a long history of using Amnesia, and I really like it. But it has its issues. Its backend isn't great. It doesn't scale up very well, and it really doesn't deal well with partition networks. So I'm trying to build something which is Amnesia-like, but planning to use InnoDB as a storage backend. Yesterday there was a talk about using LevelDB. I think both are good candidates. Yeah, and try to come up and find a way to solve this, how to deal with partition networks. I think the talk, Benoit, sorry, I got your name correctly, mentioned earlier about Primer. There was some idea, actually a lot of things I thought about, there was a lot of overlap between what you're trying to do in Primer and what I have in mind with this, so it'll be interesting to see what all we can steal out of that. Bounded message queues, again, this is a long-term itch of mine. I think back in 2003 or 4 on the mailing list I said, one of my systems went out of control, the processes, because the message queue built up. Can we have an option where I can say this process should have a maximum message queue size of, say, 100 or 1,000? And I got told off by all the Erlang gurus saying, no, that's just bad design. Go back and think about how you're designing your stuff. But I still think it's a good idea. Thinking a little bit about it, it seems fairly straightforward to achieve in that, you pass in an option, and there's a couple of BIFs you have to modify, and you should just be able to kill the process if it exceeds the maximum configured limit. We can't throw away a message because that would violate Erlang semantics, but killing the process is fair game, right? That's what you're supposed to do in Erlang. So that's something we're looking at. The other thing we're looking at is, yeah, but if you think about it, if you look at a system which sort of becomes unstable because it has built up a message queue, most often the only way to recover out of that is either restart your node or kill the process. So, sorry? Yeah, I mean, flush the queue. Okay, how do you flush the queue? I mean, the reason the queue is built up is because the process is not able to process it fast enough. So if by flush the queue you mean throw away the messages, well, it's the same thing. Do you kill the process? Well, it's still the same thing. You're still throwing away messages. Other than taking traffic away from the system. So you route traffic away from it so that the process has a chance to catch up. But sometimes the message queue is built up because the process, as part of doing work with that message, is calling maybe an external system or calling another process. If it's doing anything non-trivial, there is no easy way to make that process recover. Yeah. I mean, that is true. You could do that, but again, sometimes you can't have a pool of processes purely because of the nature of the work. Because you got to do it sequentially. Like in our case, the messages which are coming out have to be held. Processed sequentially before they can be fanned out into that tree. Sometimes there's that dependency. Um, I mean, my point about having an option like that is sometimes you put a system into production because you haven't foreseen um, these message queues building up. And typically what happens is if when such a thing happens, it's it takes a lot of manual intervention to recover that system back into a working state. Um, and it dies a slow, painful death because actually you've got a lot of RAM on the box, so the message you can build up, without before anyone has noticed it. Um, yeah, I agree. I agree. I mean, which is what I did, which is what we did in the end. But but my reason for wanting such an option is more to make it easier to detect it and recover faster from it. Sometimes systems are built without thinking about that back pressure, or someone hasn't foreseen that that kind of load can happen. Um, yeah, but that's a lot of extra. Yeah. I mean, I know you're right. It is an option, but it just seems cleaner if the beam process can say you die if you're not allowed to
Mm.
exceed more than a certain amount.
Why not? Why are you not using the ETS buffer as a full FIFO queue? So the worker, rather than getting the message, will just be fed by themselves from the buffer. Just to keep the queue in the queue rather than trying to kill it if the message queue is exceed the max. Just put everything in ETS, multiple ETS, not only one, and then stop when the limit is achieved.
Yeah, I mean and as you've seen, that's what we do. We use ETS as pretty much a message queue, but not a.
Yeah, but before you're still sending message. So my point is to stop the concurrence, to stop sending message, and rather than using worker as a pull, uh, just pulling from multiple ETS each time.
Sorry, I don't
Yeah.
understand. Maybe we can discuss it later. But yeah, I mean, yeah, all the points you've raised are valid. But the thing is, we can be aware of all these safeguards and workarounds and things, but sometimes systems go into production where these things haven't been thought of or someone hasn't foreseen it. And my view is that actually, if a system is going to die, I'd much rather it dies quickly so that when it recovers in a clean state. What the worst thing is something which just takes time to, a slow, painful death. I wouldn't wish it on anyone, so not my processes either. Um, Deep packet inspection. Again, this is we're trying to understand the kind of traffic patterns we are getting into our network in real time, because that's quite useful to us. Um, Again, obviously this can quite easily be done in C. You can do wire speed packet processing, all that. But actually, for some of the things we want to understand, it's much easier to express that in Erlang code rather than having to write it in C. So we're trying to, our R&D team is looking at a way of taking the fire hose of traffic coming into our network, but then doing some deep packet inspection on it. And we'd love to do it in Erlang, but again, we have to see if we can keep up with those message rates. Yeah, I mean, speed will be an issue. So yeah, again, message from my employer, as Kevin said earlier, come work with us because doing lots of interesting stuff with Erlang. I'm open for any questions.
We have 3 minutes for questions.
Yeah, I mean, I think. Yeah. Exactly. Yeah. Yeah, and which is yeah. No, they just said it would just work. Yeah, yeah, but I think if that is the, if we're going to see more and more servers with more and more memory, I think it would probably be good if Beam could actually natively use huge pages. That would be a huge boost, especially for. Yeah, I mean, especially if you're gonna have in-memory database which cache a lot of data, then it would be very useful. Yeah, that's the thing. It's not at all obvious that it's doing something. So sorry, are you saying that as of R16, the Beam VM already? Right. Okay. Right. Yeah. I mean, it's good to hear that others have also observed this, because that was the first time we had encountered it.
Okay. I think we are good. We can continue the discussion right after, because we will miss the Erlang's things.
Okay. Thank
yeah,
you.
Thank you.